last class we have considered okay, this is the primal problem is given. Let us assume that its solution is given x star is x1 is 20, x2 is 60. We want to use that whatever the theorems we have studied it, use that theorem to find out the dual solution directly from the primal solution. And we have seen using this equation A and B, we have ultimately we have solved and got these values that y star is equal to 1, y 2 star, last class we have written 2 solution of it will come 1. So, our solution is y star is 1, y 2 star is 1 and y 3 star is 0. So, if you find out the objective function value in dual problem, that will come, if you see the expression for that one, that f d 80 into y 1, this is 80 into y 1 star plus then your 100 into y 2 star, 100 into y 2 star plus then you say 40 into y 3 star, 40 into y 3 star, then y 3 star value is 0. So, now y 1 star value is 80, y 1 star value is 1 and y 2 star value is your 1. Okay. So, this value will objective function in dual problem it will come 180. Similarly, if you see the primal problem objective function values, that primal function objective function is z p is equal to you see 3 x 1 plus 2 x 2. Okay. This is our objective function of the primal problem, and we have given x 1 star, you see here the value of x 2 is 20. Solution of primal problem is maximization of the objective function. At what point we will get the maximum value of the function, x 1 is 20, x 2 is 60. If you put it here, that 30 into 20 plus 2 into 60, so its value is 180. So, objective function value in dual problem, that maximization problem value is same as the dual problem minimization minimum value of the objective function value is 180. Both are same at optimal conditions, mean optimal point in what is called primal domain and as well as in what is called in dual domain or dual domain. Okay. So, today we will discuss about the solution of what is called quadratic programming problem using the simplex method. Okay. So, let us take in one example, and through example we will explain that how we will solve the quadratic programming problem using the simplex method. So, let us consider that our what is called function is minimize f of x, that is we have to minimize, is equal to x 1 minus 3 whole square plus x 2 minus 3 whole square. And if you expand this one, we will get it here x 1 square plus minus 6 x 1 plus 9 from this factor, and from this factor it will x 2 square minus 6 x 2 plus 9. And if you simplify this one, x 1 square minus 6 x 1 minus 6 x 2 plus 18. Okay. So, you can easily write in quadratic form like this way. You see this one I can write it half 2 0 0, there is no cross product term x 1 and x 2. So, I will write it this is this way. Okay. and this before that one will be that x transpose and this multiplied by x. Then your next is your plus minus 6 into x plus 18, which you can write it half x transpose. This if you consider as a H matrix, H which is in symmetric, in general it is a symmetric matrix. If you convert it into quadratic form into x plus this if you consider as a C transpose, that C transpose x, agree, plus what is the remaining term is left in this expression 18 plus this I am denoted by d. So, this one the objective function which is expressed in quadratic form, that one, and a function is in quadratic form and this function is a objective function is a quadratic and convex. If it is a convex, the what is called Hessian matrix of this function should be positive semi definite. Okay. So, which if you take the what is called Hessian matrix of this one, second derivative of this function, then it will come only capital H. This term will come in 0. So, now this is the problem which is we have converted into a standard what is called quadratic form, which is a convex function in our problem. So, subject to there is inequality constant and what is called equality constant x 1 plus x 2 is less than equal to 4. Agree? So, all inequality constants, if here only we have one inequality constant, in general if we have a number of inequality constant is m and number of what is called equality constant is p, then we can write number of inequality constant in matrix and vector form. Let us call this we have represented into A transpose into x is less than equal to our b, that this the inequality terms right hand side what we have get it, that is b. So, and where our in our case x is what, there are two decision variables x 1 and x 2. So, this is our equation inequality equation. So, if you have a inequality constraint of m such constants are there, I can always write in terms of A transpose x is less than equal to b. Now, if you have a equality constants are there, let us call you have a equality constants x 1 minus 3 x 2 is equal to 1. So, that we represent this one equality constraints by n transpose x is equal to E. Okay. And that inequality constant if you consider cross p number of equality constant, if you can consider our inequality constant is m cross 1. Okay. So, we can write it here what is A transpose in your case. In your case A transpose if you say see this one is nothing but a 1 1. This is our A transpose, and what is our n transpose here? N transpose in this case your will be 1 minus 3. Agree? So, our E is equal to in our for our example is 1 and in our case B is equal to 4. So, so we have identified what is H, what is our C transpose, agree, what is D, what is A transpose, what is B, what is N transpose, what is E, all these things. So, our in general our problem we will write it like this way: minimize a function f of x which is a half x transpose h x plus c transpose x plus d, d is the constant, subject to A transpose all inequality x transpose x is less than equal to b, and b is the dimension of vector is m. There are m such inequality constants are there, which is combined together is this, and equality constant n transpose x is equal to a, that we consider m p cross 1. So, now these problems can be solved by using simplex method. First, what is the necessary condition that this function should have a minimum value? At what point this function has a minimum value? This function means quadratic problem, that function or quadratic which is a convex in nature. So, what is the necessary? So, one can easily find it by using KKT conditions. So, let us write it first, that Lagrange function, and if you recollect, we have discussed in details the Lagrange function, how to generate this Lagrange function. So, Lagrange function L is equal to our objective function. What is our objective function? X transpose h x plus c transpose x plus d, this is the objective function. Then that inequality constants, then equality constant. So, we have a equality constant, let us call we have a equality constant lambda transpose the Lagrange multiplier. I am just following what we have discussed earlier, the KKT condition to find out the optimum value of an objective functions. So, our equality constant is n transpose x minus e. So, this quantity is 0, at what point we will get the optimal value or feasible solution of this one. Okay, it must satisfy this is equal to 0. So, a lambda transpose of this plus then you have a mu transpose Lagrange multiplier is a vector, mu transpose that multiplied by A transpose x plus s minus b. So, A transpose x minus b is less than 0. So, you have to add some what is called variable, okay, and that variable is called the variable what we have considered, that variable should be some positive value. So, that this equal to 0. So, this variable is called the slack variables. Okay. So, this because that means you have to this is the surplus variable, that means we have to add this one x transpose x minus b is less than equal to 0. So, you have to add some value of this one. So, this is the you call what is called slack variables of this one, and when this will be greater than equal to 0, that means this is a positive quantity, you have to subtract something. So, that is called surplus variable. So, in your case it is a slack variables are there, this and this value is greater than equal to 0, but this Lagrange multiplier associated with the equality constraints, that sign is unsigned, this value may be positive or negative. For all types of inequalities x transpose x minus b less than equal to 0, we have proved it that mu should be greater than equal to 0, Lagrange multiplier would be greater than equal to 0. In reverse type of inequality, for reverse type of equality means A transpose x minus b is greater than equal to 0, that type of things, then our mu should be less than equal to 0. That means non positive numbers in that situation, but our case is A x transpose A minus b is less than equal to 0. So, it is a non negative numbers. So, keeping, let us call this equation is equation number 1. Okay. So, now we can easily write the necessary condition KKT necessary conditions to have the minimum value of the function necessary conditions. So, what is the necessary condition of KKT? Del L Lagrangian function with respect to x, you have to find out. Now, see this, our objective function is this one. Now, I am differentiating this thing with respect to x. So, x transpose h x, if you differentiate with respect to x, that will be coming twice h. Second if you differentiate this one with respect to x, then it will come twice h x. So, twice x h, and it is a half is there. So, it will be a coming h of x. The next time you see C transpose x, if you differentiate this one, then it will come C only. That is, we have discussed earlier, if you recollect these things. Then similarly, if you this x term is involved first of this bracket first term, agree. So, lambda transpose n transpose x, this is no x variable, lambda transpose E, no x is involved. So, that term will be 0. So, here this will be a, I can write this one, if you see this one, I can write n lambda whole transpose x, this quantity I can write it this form. Now, differentiate with respect to x, that will be n into lambda only. So, that will be n into lambda. Similarly, this x term involved in the first, second and third, there is no s term. So, if you partial differentiation of that term with respect to x, we can write it this one, this mu transpose A transpose x, we can write it equivalently into this form, A mu whole transpose x form. Then you differentiate with respect to x. If you differentiate with respect to x, you will get A mu is equal to 0. Now, see this one, and how many equation you will get it? There are n equation is like this way, and we have used this property when we are differentiating this with respect to we have used this property x transpose p x, when differentiate with respect to x, we will get it twice p x. Then we have a c transpose x, when differentiating with respect to x, the result is c. That is, we can verify by simply principles of what is called differentiation of a scalar quantity with respect to vector, the way you did it. So, this is the first we got it. Next equation, necessary condition of KKT, differentiation this with respect to mu assigned to 0. Now, mu term is involved in only in the this term. So, if you differentiate with respect to mu, that will come, what will get it for this one? Mu is a vector of that one, you will get it, and this whole quantity is a scalar quantity, that will come A transpose, using this property you can write A transpose x, A transpose x plus s minus b, because you are differentiating with respect to mu, A transpose x plus s plus b is equal to 0. This is this term is constant, or you can say this one, because this is a scalar quantity, you take transpose both side, it will come whole transpose that mu. Now differentiate with respect to mu using that property, it will get that one. So, and note here, and note that our S is equal to, we defined S, how many inequality constants are there? We have a m equality constant, that each component of this we defined like this way, if you recollect our earlier case, this one, and how many this equation will be? This is m cross 1 equation. Next is we have to differentiate this with respect to lambda, the Lagrange multiplier with respect to lambda. So, lambda is associated with this term. Okay. So, since it is a scalar quantity, take the transpose, then you differentiate with respect to lambda, partial differentiate with respect. So, that will come, it will be n transpose x minus E, and how many equation will be there? Equality constants are there. There are p equality constants. So, we have altogether n plus m plus p equation. So, this equation we have, in addition to that, we have a switching functions that we have seen earlier, then del L you differentiate with respect to del S. Okay. So, this if you differentiate with respect to S, this is a S square, this S, each m component of this one is S square, I am differentiating with respect to S. So, this will get it twice mu I, see this one, this. So, each component will be mu 1 S 1 square plus mu 2 S 2 square plus mu 3 S 3 square. So, I am differentiating with respect to I. So, there will be twice mu I S I is equal to 0, and I is equal to 1 2 dot dot, this is associated with the inequality constants. How many equality constants are there? M. So, this I can write further, I can write it this mu I S I whole square, both side multiplied by S I is equal to 0, I is equal to 1 2 dot dot m. Okay. So, if you give the equation number, this is equation number 2, this is equation number 3, this is equation number 4, and this is equation number 5. And note that lambda is free in sign, no restriction on its sign, no restriction in sign. In the earlier we told it beginning of the statement. So, you have a 5 equations are there. In addition to that, if you want to solve this by using the simplex method, that we have a lambda also one of the variable in the expressions. So, this I can write it, that next is note lambda is free in sign. So, you can write it lambda is equal to lambda. What is the lambda associated with equality constraints? How many? What is the dimension of this one? P cross 1. So, lambda I can write it y minus z, each is p cross 1, and each component is greater than equal to 0. This is also greater than equal to 0, positive condition. The difference of this one may be positive, negative, and 0. This. So, this is the our new variables we have introduced. In place of lambda, I will write it y, which is greater than equal to 0, minus z greater than equal to 0. So, we can reformulate the problem now. If you just see, we can write it this equation. Equation number 2, 3, 4, 2, 3, 4. I can write it. Now, see this one, equation number 2, what we can write it? H. So, what are the vectors are involved? X unknown, lambda is unknown, mu is unknown. I will rearrange first x, then mu, then lambda. Agree? And you have a S also, this S also you have, and S, what is the dimension of S? You have a m cross 1. Yes. So, I will just rearrange in this way, first x, then mu, and then S and mu in the same expression S, then y, because lambda has the two parts, If you see the lambda, we have two parts y and z. Accordingly, I will write it. So, first expression h into x. So, I am just writing it here. So, I am arranging this one x, and what is the how many decision variables of x are there? N cross 1. Side by side I am writing the what is called the dimension also, so that it is easy for our to track this equation. So, next I will write mu. What is the mu dimension? M cross 1. Mu is m cross 1. Then I will write it s. S is a vector whose dimension also m cross 1. So, I will just partition. Then I will write it our lambda. Lambda has a two parts y and z. So, y I am writing this dimension is m cross 1, then another is your z p cross 1. So, this is our all unknown variables. How many unknown variables are there? N, m plus m, n plus twice m plus twice p. This is the unknown variables are there. So, from equation number 2, what we can write it? C. This is the constant. This is we know from the description of the problems. So, I will take that is in the right side of the equation. So, h x, h multiplied by x, then you see next variable is mu, mu multiplied by a multiplied by mu, mu is a vector, column vector. So, a multiplied by mu, a multiplied by mu. So, this I have written it. Then lambda, n multiplied by lambda, lambda is y minus z. So, there is no s here. So, I will write this value of s is here 0, and that is lambda is n into y minus z. So, y is involved with n, z also will be involved with minus n. So, I will write it n, then partition minus n. So, let us write this dimension of this one, and what is the how many equations we will get it from the first equation number 2? How many equations? There are n equations are there. So, we have here to here n equation, and this is n, a into mu, a dimension is n and mu dimension is m. This is also same as s dimension same as mu. So, this is also will be m, n into p, n into p, this dimension n dimension is n, and this is a p, and this is also p. So, we know this block. So, this is the corresponding to, I can write this corresponding to equation number 2 is equal to, what is the right hand side? Right hand side is equal to c. If you take that as a minus c, so minus c, and what is the dimension of this c? What is the dimension of this one? It is a n row and 1 column. Okay. Now, write it, it is a second equation, A transpose x. So, x corresponding to A transpose. Then you see there is a s, and this is the constant term from the description of the problem, you take it right hand side b. So, s is next component is 0, then it is a s I, because s into I can write it always I into s, this I can write I into s, and other terms is 0, 0, this, and this term is equivalent to b, and b is the number of inequalities, right hand side of the b is the right hand side of the inequalities, that dimension is your m. So, this dimension is also will be m. Now, what is that? This is equation 2 corresponding to equation number 3 we have represented. Now, see equation number 4. See equation number 4, that this is the E, n transpose equality constant n transpose x is equal to E, it is a constant term, to take it right hand side. So, then if we have a only n transpose x, so first block will be, this first block will be n transpose, and other elements are 0, 0, 0, 0, and if you take the right hand side of this one, it is a E, and how many inequality equations are there? P. So, this also will be P. So, we know the whole description of that one, that means if you consider the whole matrix is B, the B dimension of this one is how many rows are there? N into M plus M P rows. If you see this one, the rows of that one is N plus M plus P. So, this dimension is N plus M plus P, this one, into number of columns N twice M plus twice P. So, this is the matrix, the whole matrix which we have got it obtained from KKT necessary conditions, agree, KKT necessary conditions, and that dimension of this one, let us call this I am calling capital X, and that capital X dimension n, first n components of x, then m components of mu, s components of s, then y component y, p components, z p components. So, this x as a dimension n plus twice m plus twice p, agree, and that must, and this is equal to, I consider this one is your D, and this D dimension is, if you see how many rows are there, n plus m plus p. So, this dimension is n plus m plus p into 1, that number of rows is 1, agree, number of rows is 1. So, now see this one. Now, if I write it this equation, now I can write it h into x 1, h into x 1 plus a into mu n into that is y minus n is equal to y, or you can say this one directly, what is this equation stands for? Put the value of h, put the value of c, put the value of n, and put the value of a in this expression, then you will get it, this expression. Let us call, I am writing it, first necessary condition h into x plus n into lambda, lambda is y minus z, that one, agree, plus a mu is equal to minus c, agree. So, H is what? If you recollect this problem, that our H matrix is that one, our H is, if you write it H 2 2 0 0, the diagonal matrix, that is our 2 0 0 2, our x is what? X 1 x 2, this is from equation necessary condition from 2. Then n is what? In our case n, if you see this, our n is, where is the inequality constraints? Equality constraints, this is our n, n is, n transpose is 1 minus 3, So, this will be a n will be 1 minus 3. So, n will be, you are writing n is 1 minus 3, then it is y, that our y is, there is a only one, that is, this is the lambda, that there is a only one what is called equality constant. So, that dimension is, in our case, is 1, for our particular example is 1. So, I can write y, then minus sign 1 minus 3 z is dimension is 1 cross 1, because we have a only one equality constants, and A matrix is, you see, A transpose is 1 1. So, it will be a column vector 1 1, and mu, we have a only one inequality constants, this equal to C value is C. What is the value of C here? That minus 6 minus 6. If you take the C transpose is minus 6 minus 6. If you take the transpose of that one, it will be a what is called minus 6 column wise is equal to minus 6 and that preceded with minus 6. So, it will be a 6 6. So, write more details, 2 x 1 plus y minus z plus mu is equal to 6, one equation. Agree? The next equation, twice x 2 minus 3 y plus 3 z plus mu is equal to 6. So, this is this two equation we got it from the equation number 2 of KKT conditions. Agree? Or directly, if you write it this one directly after that notation you are familiarized, you directly from this equation if you write it, you will get two set of equations, that is n is equal to 2, we have a two equations, we will get it here. Next, m is equal to 1, number of inequality constant is 1, we will get one equation from this one. What is this one? If you say A transpose x plus s. So, A transpose x, A transpose is what? A transpose, our A transpose is 1, you see our A transpose is 1 1. So, if you write it A transpose from this, from third equation KKT, from equation 3 is your, you can write it A transpose x, A transpose is y 1, A transpose is your 1 1 into x, x has a two components x 1 and x 2. Agree? So, next is your s, s is a, there is a only one inequality constraint. So, this will be a your I into s is equal to, say, is equal to b, that is equal to this equal to b, or second equation of this one you say A transpose x plus s is equal to b. So, b value is what? From the problem of B value is our 4. Okay? We have a this equation, this equation, this equation. Then another equation we will get from 4, KKT condition from 4, and 4 condition is n transpose x is equal to E, n transpose x is equal to E. So, what is n transpose? N is what? N transpose is what? 1, see this problem 1 3 into n transpose x, n transpose x, x is x 1 x 2 is equal to our E. E value is what? From the statement of the problem, you just see the statement of the problem, our E value is given to 1, E value is 1. So, this equal to 1. So, if you make it this one x 1 minus 3 x 2 is equal to 1. So, our KKT conditions all are, if it is a quadratic programming problem, that our KKT conditions is coming a linear form. All equation is linear. In more general is b into x is equal to d form. Agree this, and where we have seen also it is a linear. Now, instead of using y, z, mu, s, we can just continue the variables in terms of x 1. So, you have already have x 1, x 2. So, if you consider next variable is, if you see the way we make it argument of this one, next variable will be mu. Mu, how many components are have a mu? M components. So, I will consider up to x 1, x 2 dot dot x n. Next is x n plus 1 is equal to mu 1. Next is x n plus 2 is equal to mu 2. In this way, last element of mu will be x n plus m. Similarly, these variables, how many variables are n? M variables are there. So, the first element of the S I will represent as a x n plus m plus 1. Similarly, second element of this one I will define as a new variable x n plus m plus 2 in this way, and similarly we can continue this way. So, if you redefine, if you define this one now, then what we can write it, and if you define this one, what we can write it, you see x, and we have another constants are there, switching constant mu I or mu j as j is equal to 0. That is what we got it, mu j as j is equal to 0, that what we got it, and j is equal to 1 2 dot dot m. Agree? So, now what we can write it from this equation, what is the position of mu? See the position of mu. If I express all the variables in terms of x, then first element of mu will be x n plus 1, second element of mu x n plus 2. So, if it is so, I can write it x n plus j multiplied by, see this one, elements of this one, the elements of this one is s 1 square, s 2 square, all these things. What is the first element of s in terms of x? X n plus m plus j, means first element is 1, x n plus m plus 2 will be the second element of s. So, if we in similar manner I can write it x n plus m plus j is equal to 0 for j is equal to 1 2 dot dot m. Agree? So, this I can write it this one. What we did it, we assign, now I am writing it, we assign that x n plus I is equal to mu I, and I is equal to 1 2 dot dot m. Agree? That x n plus m plus I is equal to s I square, and I is equal to 1 2 dot dot m. And what we assign it this one, y z, y and z, x n plus m plus m, twice m. So, I can write it x n plus twice m plus I is equal to y I is equal to, because we have a how many in general, p equality constants. Agree? So, next we can write it that x n plus twice m for z plus p plus I is equal to z I. is equal to I is equal to 1 2 dot dot p. So, these are the variables we have defined in place of mu, s, y and z. Okay. So, our problem now boils down to solve a what is called linear equation, that this linear equation we have to solve it. So, recall this equation, b into x is equal to d, okay, and this dimension of this I have just mentioned you earlier also. This dimension is n plus m plus p, this multiplied by that n plus twice m plus twice p, this into 1. So, this dimension is this into twice n plus this dimension is n plus m plus p, this is a p plus twice n, and what is the dimension of that one? N plus twice m plus twice p into 1. See what I have written it here, explained it there, same thing I am writing it in this case, because it is a column vector, that is 1 will be there. Okay. So, what is our d? D dimension is n cross m cross plus this cross 1, and this one we have to make Bx is in such a way all right hand side of this one is positive quantity. Okay. So, now how to solve this one using that simplex method. So, first you say that our quadratic programming problem using KKT necessary condition, we can convert Vx is equal to d from linear set of equation. Now, question is this linear set of equation we have to solve by what is called by simplex method. We have introduced new variable in place of mu, s, y, lambda is replaced by y and z, that we have replaced by new variables x. Okay. And then question is how to solve that one. Next questions. So, this problem so to solve the problem using simplex method. So, we do not have any objective function here, because only from the KKT necessary condition we got set of linear equation, and we have to make in such a way that it is a standard LP problem form. Agree? But still now it is not a standard LP form. I can make right hand side of the equation d always positive by some manipulations. Agree? So, our b into x plus p is equal to g. So, I have introduced some artificial variables which is a vector, the dimension of this one is same as dimension of d. So, this dimension is n plus m plus p cross 1. Okay. So, this dimension you know, this dimension you know, this dimension you know, and this p is a vector which is artificial variable. Agree? Whose element is greater than or equal to 0, artificial variable of dimension. This p is a vector whose elements are the artificial variables, and each element is greater than or equal to 0. This. So, you can write it, the p is nothing but our p 1, p 2 dot dot p n plus m plus p, this one, and this dimension of this one, this dimension of this vector is that one, n plus n plus m plus p cross 1. So, now we have just introduced some artificial variable, so that this equal to ultimately artificial variables value must be 0, this one. So, when we have introduced the artificial variable, we know the sum of the all artificial variables is our objective function. So, W is nothing but our objective P 1 plus P 2 plus dot dot P n plus m plus p element. This is our objective function. That objective function is called artificial objective function. Then how will you get the function value in terms of x parameters? That P 1 I can always write the first element of P 1 I can always write in terms of x and d elements. So, P 1 is expressed in terms of take b x in the right hand side and element wise P 1 P 2 wise you equate, and then you add P 1 P 2 all these things. So, ultimately this you will get a function of all decision variables, agree, and this decision variable not only decision, it is a decision variable, then Lagrangian multipliers mu lambda associated with this one and s with this one. So, you know how to solve this one. Let us call that one what is called precaution or one observation one must note, that we know this, we know mu into s square is this equal to 0, agree. So, both this product of this one, both product cannot be non negative. That means, if one is non basic variable, other must be both the elements cannot be what is called basic variables. That is, if basic variable value is what is called non-zero. So, this if it is a non-zero both the things, then it cannot be, product cannot be 0. So, one can see the product of these two things for j is equal to 1 on this, both variables this one and this one cannot be a what is called both basic variables. Either one of these must be a non basic variables in general. So, note that x n plus j and x n plus m plus j are not simultaneously the basic variables. Okay. So, the problem given in this one I can easily solve by using the simplex method. If you just want to solve this one, you can solve it in simplex method. So, in your case, how many variables are there? If you see in your case this one, how many variables are there into that mu s y z, n twice m twice p, n is 2, m is 1, 2 m, 2 plus 2 4 plus 2 6. So, we have a 6 variables are there and 6 variables are there. So, if you just put the tabular form, I can easily write it now x 1, x 2, x 3, x 4, x 5, x 6, agree, this x 6. Then we have a how many, we have a what is called vector of artificial variable. There are 4 artificial variables are there, because we have a 4 equations are there, the set of linear equation. Artificial variable is 4, x 7, x 8, x 9, x 10, then b, then your ratio, you write ratio, the standard way, and our basic variables are what? Basic variables in this direction. Our basic variables is x 7, x 8, x 9, x 10, and then our artificial objective function you can fill up. Agree? According to our problem, if you filled up this one, that I am just writing it this one to from the equations, from the KKT equations what you got it, and we have written this equation. If you see this equation, this equation, if you write it in terms of z mu in terms of x, if you write it, you will get it 2 0 1 0 1 minus 1 1 then 0 0 0. Agree? Next is 0 2 1 0 minus 3 plus 3 0 1 0 0, and this b is 6, this is also 6. Then next is 1 1 0 1, then 0 0 0 0 1 0, and last equation 1 minus 3 0 0 0 0 0 0 0 1, and that right hand side is 4, this right hand side is 1. And the cost function, if you see, minus 4 0 minus 2 minus 1 2 minus 2 0 0 0 0, and that is W. So, next class I will complete, not complete, I will explain how you have to proceed and get the solution of linear quadratic regulator programming problem using the simplex method. That is basically from KKT condition we have converted into a linear set of equation for quadratic programming problem only. So, here I just stop this one.